This is the third video in the video series of limits, and this one's a short one on the properties of limits, and it's going to be pages 16 through 19 in your notes. So here's the properties of limits. The following list the properties of limits are important in our computations with limits. We have been using these properties, so most of you it should come as no surprise. So I'm going to go through each one here a little bit first. The very first one here says if b is a constant, then the limit b times f of x, give the b here, you can bring the b out front and put it in front of the limit. So here's the example. If I have the limit of 5x as x approaches 3 is the same as saying 5 times the limit of x, and 5 times 3, as you put the 3 in there, would be 15. So it works for both of them. The second property is if I had two limits added up and they were approaching a constant, it's the same as splitting them up. And here you have, I'm approaching 3 of x squared plus x. That's the same thing as saying the limit as x approaches 3 of x squared plus the limit as x approaches 3 of x, and those would add up to get your 12. This one is multiplication. So if I have two functions multiplied inside, I can split the limits up and also multiply them if they're going to the same constant. And here's the example for that. And division works the same way. If I'm doing the limit as I'm going between these two that are divided, you can actually split them up and do the limit of the top divided by the limit of the bottom. And I gave a numerical example of that. And then for any constant k, if I'm approaching another constant, even if x approaches 3 of 7, it's always going to be that constant 7. And then as x approaches a constant c here of x, it's always going to be the constant. So if I plug in a 3 here, I'm always going to get it. So I kind of gave you an example, told you the property, and gave you an example. Okay, a lot of them make sense, but I wanted you to have it for your notes. Now the next part is important, and we're talking about limits from the left and limits from the right. So if we were going to look closely at the limit as x approaches 0 of radical x, so I'm going to draw a little graph here of radical x. So here's the x value and y value of our equation. If I were to graph it, it would look like this. And we said earlier in this course that it only can be defined for x is greater than or equal to 0. So if you see, it's only here to the right side of the y-axis. This is illustrated in the graph. Notice that no function is graphed to the left. So here this function does not exist. Well, what happens at 0? We do not define radical 0 equals 0. Does this function have a limit at x equals 0? So basically they want to know, does it have a limit right there? Okay, right at the beginning point of that. From our previous notes, we would say that we have a limit at x equals 0. As x gets close to 0, radical x gets close to that limit. But what if we choose negative 0.0001, a number close to 0, but on this side of it? Okay. The problem is that negative 0.001 is negative, and we know that radical x is not defined or undefined when x is less than 0. With this function x, we can get close to 0 from the positive side, but we call this a one-sided limit. It only goes on one side because you can only define this function from the right side. Okay, so let's look at how you define if you look at a limit from one side. So basically what you're going to see here, and I'm going to write a little bit bigger, the limit as x approaches some constant, and if we approach from the right side, you're going to see a little plus sign of this function. If we approach from the left, the limit as x approaches any constant from the left, you'll see a little negative sign of f of x. Okay? If the limit from the right equals the limit from the left, then we can say the general limit from both sides exists. So they both have to equal each other for the general limit to exist. So let's look at this graph here to determine if each of these limits exist. So I made this graph here. I've got a piecewise function, so I have part of the piece comes here, and this is 1, 2, 3, by the way, and a part of the piece comes here. This is an open circle, that's a closed circle. Okay, so this kind of illustrates this. First of all, we notice that this is a not continuous function because there's a hole in the graph. I pick up my pencil. So continuity is important. So if I'm gonna, the limit of f of x as x approaches 3 from the left. So if I'm coming from the left, I'm gonna follow this line down right here, okay? So I'm gonna kind of do a little highlighter here. So if I follow right coming from this way, do you see? I'm approaching 1. See how this is approaching a 1? So I say, okay, when I come from the left, it's 1, all right? Now I'm gonna do a little medium thing, and if I approach it from the right, I approach this right here, and this is 1, 2, 3, 4, 5. So when I approach from the right, my y value is 5. If I approach from the left, my y value is 1. If I look at it here, the limit as x approaches 3 of this function, I'm going to say does not exist, because the limit from the left, the limit as x approaches 3 from the left of this function does not equal the limit as x approaches 3 from the right of this function. If they don't equal each other, the general limit, meaning from both sides is what that means, does not exist. Okay, let's use this piecewise function below to determine each of the limits if they exist. So now I don't have a graph, but I have a piecewise function. So we're going to approach 4 from the left. Well, this is x is less than 4, so this is approaching 4 from the left. So we learned that you just substitute it in. That's the first thing you do. So I'm going to do 2 times 4 plus 1. Even though 4 is not included, I'm still coming, this is all values less than 4 up to 4. And when I get that, I get 2 times 4 is 8 plus 1 is 9. So my point would be actually 4, 9, that you would approach but not quite get to that. Now if I approach it from the right, these are all the numbers greater than that. I'm going to plug a 4 into that one. So when I do, I have oh, it's not letting me write right now. Excuse me, guys. See if I can get it to write. Sometimes it does this to me. So if I plug a 4 in, let's plug a 4 in there. I got 4 squared is 16 minus 7 is 9. So this is also 9. Please write a 9 here. So I can just say now the limit exists, the general limit exists, because when I go from both sides, it is 9. So this is 9 right here. Excuse me. This comes out to be 9 when I plug in the 4 squared minus 7. And then I can say the general limit is 9. And I just made this, and we practiced in this in class with continuity. We just made this continuous because the point 4, 9 is on, it connects at 4, 9 and continues on. So that way I can say the general limit exists. There's one more example here. And here's another weird looking graph, so I thought we could practice. Okay. So let's look at approaching this function from 2 to the left. So I'm going to come this way. So as I come from the left, I have to stop and come here. When I approach 2 from the left, as you see, my y value is 1. So I put a 1 here. Now I'm going to approach 2 from the right. So I'm going to come this way. I'm going to follow the function up. Come here. When I approach 2 from the right, it is also 1. Even though the point 2, 1 is not on the graph, it's the point 2, 2. See, that's called removable. There's a limit. So now I can say the limit as x approaches 2, the general limit is going to be 1 because the left and the right match. Even though the point 2, 1 is not there, I'm approaching 2 on both sides. Now let's look at approaching 4 from the right. So if I approach 4 from the right, there is no function there. So I have to say that does not exist. There isn't anything to the right of this graph when I come to approach 4. If I approach 4 from the left, I'm following my function coming up here. I approach 4 from the left, I have a 1. And because the left and the right do not match, I said the general limit as x approaches 4 of this function does not exist. Okay, so if you'll notice, you can do this over and over again. Let's try one here. Let's do one at 1 because I didn't do it here at 1. So if we did the limit as x approaches 1 from the left, and then the limit as x approaches 1 from the right of this function f of x, because you always have to put the function there. Let's see if we can see if the general limit exists. So if I approach 1 from the left, my y value is 0. If I approach 1 from the right, it's 1. Therefore, the limit as x approaches 1 generally of this function does not exist because the left and right don't match. Well, there's a little short video, and oh, there's one other page, sorry, one more page. So when do limits fail to exist? This is a good page. There are 3 situations in which limits fail to exist. We will look briefly at this. One is if the limits, and we've just been talking about number 1, if the limits from the left and right do not match, like this picture right here, the left limit does not match the right limit, then it fails to exist, just like we looked at there. The other 2 are if f of x oscillates wildly near this c. See, if I get close to 0 on this limit, do you see how it's going up and down, oscillating wildly? If it oscillates wildly, the limit does not exist. And the third one, if the limit is infinite, the limit does not exist. So let's look at this picture here. So if I approach here, I'm approaching 0 from the left, it's infinite. See how it's going forever. And from the right, if I approach it, it's infinite. Therefore, the limit doesn't exist because there's a vertical asymptote and it's approaching positive infinity. Okay, so this one has a vertical asymptote. So you need to memorize these 3 cases that a limit does not exist. The first one we've been practicing. The second one is oscillating wildly. And the third one is if you're going to infinite, then the limit does not exist. Okay, now we're done. Thank you very much, and there's one more video left.